Problem number 5. A cylinder has a radius r and weight g. You try to roll it over a step of a height h less than r. The minimum force needed to roll the cylinder over is next one. Solution for problem number 5. Rolling the cylinder over requires overcoming the torque due to gravity. We choose the corner of the step as our pivot point, this one. The force from gravity is mg equal big G. The distance between the corner and the vertical line bisecting the cylinder is given by formula this one. So it means that total gravity torque equal G multiplied by X. To counteract this torque with the smallest force possible, we need the largest moment arm possible. The largest moment arm possible is 2R, this one, and the force applied must be perpendicular to this red line. So it means that total equation for equalize two torques equal 2RF equal G multiplied by this square root. And from here we can find what is the minimum force needed. That will be this expression. And this is answer C, and this is the solution for problem number 5. Problem number 6. A ball is released from rest above on the inclined plane and bounces elastically down the plane. As the ball progresses down the plane, the time and the distance between each collision will do next one. Solution for problem number 6. Let's work in a reference frame where with the x-axis along the plane and y-axis perpendicular to the plane. On the picture it looks like this. Then in the y direction the ball simply bounces regularly up and down because we have a constant acceleration in this direction. So the collisions are uniformly spaced in time. However, gravity provides an acceleration in x direction, so the distance will increase in x direction. And this is answer A. Time remains the same and the distance increase. So that's answer A, and that's solution for problem number 6. Problem number 7. An object of mass m is attached to the end of a massless rod of length L. The other end of the rod is attached to a frictionless pivot. The object is raised so that its height is 0.8 L above the pivot, as shown in the figure. After the object is released from rest, what is the tension in the rod when it is horizontal? Solution for problem number 7. Using energy conservation, we can find that V square in horizontal point equal this expression. But our object moving by circular motion. It means that when it's horizontal, it has horizontal acceleration equal centripetal acceleration, which could be found from formula tension equal mass multiplied by centripetal acceleration V square over L, which is using a previous formula equal 1.6 mg. That was answer B, and this is the solution for problem number 7. Problem number 8. The mass and the radius of the Earth are m and r. If an object starting at a distance of r from Earth's surface is moving at a velocity v0 equal square root from 2gm over 3r, tangentially, what is its trajectory? Solution for problem number 8. In this point, we have to compare this velocity v0 with the escape velocity and the circular orbit velocity. For escape velocity, we have this expression. We have escape velocity equals square root from 2gmr. In our case, small r equal to big R. It means that the escape velocity equal this one, square root from gm over r, which is greater than v0. It means that our trajectory, it's not hyperbola, it's ellipsis or maybe circular orbit. But next step is to compare our velocity v0 with the circular orbit velocity. For circular orbit velocity on a distance small r from Earth, we have equation that's equal square root from gm over small r, and small r equal to big R, and this expression less than v0. It means that in our case we have tangential velocity in this point, and it's less than velocity v0. It means that this is the closest point to surface of Earth. And this is the answer C, an ellipse whose minimum distance from the Earth's surface is big R. That's the solution for problem number 8.